Hello everyone, welcome to this lecture of hyperbolic geometry. In this lecture, we'll study about the isometries of the upper half plane model of hyperbolic plane. So we'll prove that the group PSL2R, it is a subgroup of isometric group of this upper half plane. So let us begin. So first, let us recall what we have done in the last class. So this is my upper half plane. This xy ordered pair belongs to R2 where this y is positive, and we have to put a metric on this upper half plane. So that metric we have called it to be hyperbolic metric. So we can say, so this is the square of line element. So dx square is equal to dx square plus dy square by y square. So this we have called it to be hyperbolic metric, or also you can call it to be Poincare metric. And now, so what will show that, so this SL2R or PSL2R, so it acts on this upper half plane with hyperbolic metric as isometries. Okay, so first, so let me define, so what do you mean by an isometry? So a homeomorphism T from H2 to H2 is said to be an isometry if T preserves line element. So that is, so T is a map from this H2 to H2. So you can write Txy equals to Uxy, Vxy. So if T is this Txy is equal to Uxy, Vxy, so then so T is an isometry if, so this formula is preserved. So if T satisfy, so if T is equal to U comma V and dx square plus dy square by y square is equal to du square plus dv square by v square. So then we call this T to be an isometry. So this is the definition of an isometry. So now let us see some example of isometry. So the first example, so if I just write down this map, T from H2 to H2, so T of xy equal to x plus a comma y. So where this a belongs to your R. Okay, so then, so this is nothing but your x plus a, and bxy is equal to your y. So du is equal to your dx, dv is equal to dy. So therefore, so this formula square of this line element is preserved. So T preserves the hyperbolic metric. So this will imply that this T is an isometry. So another example, xy to be equals to lambda x lambda y. So where this lambda, let us take it to be positive. So here, this uxy, so here it is lambda x, vxy, so this is your lambda y. So du is equal to your lambda dx. So dv is lambda dy. So now if I take this thing, so in the numerator we have lambda squared times dx squared plus dy squared by lambda square y squared, and this is equal by y squared. Okay, so therefore, this t, so here this t is an isometry of this upper half plane. So if you look into the geometry of this example 1 and example 2, so in the example 1, so what we have did, so this is my upper half plane, and if I take any point x comma y here, so this t is just a horizontal translation. So horizontal translation is an isometry of this upper half plane with the hyperbolic. In example, so this, let us write this to be t lambda xy equals to lambda x. So t lambda x, what is the dynamics of this t lambda xy? So this is lambda x lambda y. So this is just scaling. So if I take xy here, and suppose this is my origin, so if we apply t on this point xy, it will go to this lambda x lambda y. So this point goes to here. So here, so the scaling by lambda, so this is an isometry. Now in terms of complex number notation, so the first map, it can be written as like this. So tz is equal to z plus a, where z is equal to your x plus iy. And the second map, it can be written like this: t lambda z is equal to lambda z. So now corresponding to this map, tz equals to z plus a, so we can have a matrix 1 a 0 1. So we can associate this matrix. So determinant of this matrix is 1, and corresponding to this t lambda z, we can associate this matrix root lambda 0 0 1 by root lambda. So this map t lambda z equal to lambda z, so this can be again written as like this. Yeah. So again, if I take the determinant of this matrix, so this will be again equal to 1. So this gives us the hint that this SL2R, it acts on this upper half plane by isometry. So obviously I have to define the action of this SL2R on this upper half plane. Okay. So now let us define, so what is the action of this SL2R on this upper half plane? Action of SL2R on this upper half plane. Okay, so first, what is this group SL2R? So SL2R, so this is the set of all 2 by 2 matrices A, B, C, D, where this A, B, C, D, it belongs to R, and determinant of this matrix is equal to 1. So now, so I'll define take and let us take Z belongs to this H2. So Z, I'll take it to be a complex number. So this action is defined to be AZ plus B by CZ plus D. So this is definition of this L2R on this upper half plane. So now, so this is easy to check that. So if I take Z belongs to H2, so this, so if Z belongs to H2, then AZ plus B by CZ plus D H2. So where this A, B, C, D, so these are my real numbers, and AD minus BC is equal to 1. So because of this thing, so because of this, so we have a action of this SL2R on this upper half plane. So this imaginary part of AZ plus B by CZ plus D is equal to divided by mod of CZ plus D square. This is greater than 0. Okay, so this proves that AZ plus B by CZ plus D, it belongs to H2. So also we can check that, so this map is equals to AZ plus B by CZ plus D. This matrix A, B, C, D belongs to your SL2R. So this T, it is a homeomorphism. So in fact, so if you know complex analysis, so this SL2R is acting on this upper half plane by Mobius transformation. So this T is a Tz equals to Az plus B by Cz plus D. So this is a Mobius. So a Mobius transformation follows a by and in fact it is a homeomorphism. What will prove that? So we'll define another. So that P is equal to R, the isomorphic subgroup of this isomorphy of this. So let me define what you mean by R. Equal to R. So this is defined plus minus this identity quotient group. PSL toward this quotient group. So the theorem is PSL is isomorphic to a subgroup of isometry of this upper half plane. This set of all isometries. So what is this thing? So it is the collection of all isometries of this upper half plane. This is a map from H2 to H2 such that set forms a group. So what is the binary composition? It is the composition under the composition of maps. So what will prove that this is R? So this is isomorphic to a subgroup of this isometry of this. So let us go to the proof of this. So first of all, we'll produce a map. So let us write this map to be phi. Isometry of this upper half plane. This map. So it is defined to be set going to be CZ plus D. So this, so okay, so in fact, we have proved that, so this map will be an isometry of this upper half plane. So in fact, so we have a map from this PSL to R to the set of all self-homomorphisms of the upper half plane. So again, so this thing, so it will form a group. So set up all homomorphisms from H2 to H2 will form a group. So first we'll prove that. So any Mobius transformation so that is dz is equal to az plus b by cz plus d, where this ad minus bc is equal to 1, a, b, c, d are real numbers. So this is an isometry of this upper half plane. Okay, so how do you prove this thing? We prove that this p, let gamma be twice differentiable path in this upper half plane. So we'll prove that, so the length of, so claim is the length of T gamma will be equal to length of gamma. So let us write, so let gamma T, so this is equal to xt plus iyt. So T is in the interval AB. Xy plus ibxy. So where this z is to x plus iy. So now this this is this following integration a to b root over square plus dv dt square divided by of xt yt dt. So let us take this to equation to be 1, and now let us the mod of this is again equal to mod of t gamma t times t prime gamma t times gamma prime t, and this is equal to mod of t prime gamma t times mod of gamma prime t. Let us write this to be equation 2. So now tz is equal to b. Now you can evaluate this t prime z. So this will be equal to your, you can check, this will be equal to your 1 by cz plus d whole square. So here you have to use this fact that AD minus B 1. And so check this thing. Imaginary part of T of Z. So this will be equal to imaginary part of Z by mod of CZ plus D whole square. Mod of T prime Z. So this will be equal to your by imaginary part of your Z. So this will imply that mod of t prime gamma t. So this will be equal to your vxt yt divided by yt. So yeah, so let us write this to be 3. So therefore from this 3 equations, this 1, 2, 3, so what we'll get, so from 1, 2, 3, so what we'll get, so length of t gamma, so this is this integration. So let us write it again. So du dt square plus dv dt square divided by pxt yt. So the numerator is nothing but your, yeah. So from this three things, so what you'll get, so the numerator is mod of gamma prime t by yt. So this you will get from these 3 equations, and so this integration is again equal to integration a to b root over dx dt square plus dy dt square divided by yt dt. Okay, so this is the length of gamma. So here what we have proved that, so t preserves the length of gamma. So therefore, so this t is an isometry of this upper half plane. what we have proved that, so this PSL2R acting on this upper half plane by isometry. So in fact, we have proved that, so this SL2R is acting on this upper half plane by isometry. So therefore, so this image, so phi from this PSL2R, so this homeomorphism of this upper half plane, so phi of this PSL2R, so this in fact, it is a subset of the isometric group of this upper half plane. So here, so note one thing, this map phi is injective. So this you can do in the following way. So now if I just take the group SL2R, and so we have a map from SL2R to this isometry of this upper half plane. So what is this map? So this map is to take this matrix ABCD and send it to this Mobius transformation. Z goes to AZ plus B by CZ plus D. So this is a group homomorphism. So let us write it to be this map to be psi. So this is a group so what will be the kernel of this map psi? So what is this thing? If I take psi of A, B, C, D to be this identity map, so identity Z is equal to Z. So this map, so this means that, so AZ by CZ plus D is equal to your Z. This implies that AZ plus B is equal to CZ square plus DZ. So that is CZ square plus D minus AZ minus B equals to 0. And this equation holds for all Z belonging to this upper half plane. So therefore, so because this equation holds for all Z belongs to this upper half plane, so this implies that C equals to 0, D minus A is equal to 0, and B is equal to 0. So this implies that A is equal to D and C equals to B equals to 0. And also, so this ABCD, it belongs to SL to R. So we have this thing AD minus BC is equal to 1. So this implies that A is equal to D. So A squared is equal. So this A, so this implies that, so D will be also equal to your plus minus 1. So this ABCD, so this matrix, so this will be either your identity matrix or this matrix minus 1 times the identity matrix. So this, yeah. So therefore, so what we have proved that, so this kernel of psi, so this in fact is this subgroup. So therefore, so what, so we have this diagram. So this is my quotient map, PSL to R. This map is psi, and this map is phi, and so this commutes. So phi compose Q is equal to your psi. Yeah. So from this discussion, so what we have, so this phi is in fact is a monomorphism. That is, phi is injective homomorphism. So yeah, so because phi is a injective homomorphism, so this implies that this PSL R is isomorphic to a subgroup of isometric group of this upper half plane. So I'll stop here. So in the next lecture, we'll learn about the geodesics of this upper half plane.